Uh, Welcome to the third week of the course. So today we are going to discuss another important operation on vectors, which we will call as cross product. And then if you recall, when we started this discussion in the first lecture, we said we will discuss some geometric features and so on. So now once we define what is this cross product, we will be in a position to talk about the equations of lines and planes and some other features in the language of vectors. Okay, so basically this is what we were waiting for, to have the basics of the this language of vectors. Okay, so just keep in mind that what we know so far, we know all the basic operations on vectors, and then we saw the notion of dot product. Okay, and how is it related with the projection of a vector onto another one. Okay, so so cross product, what we do is we take two vectors. Okay, so call them u, v, and okay, have their coordinates or components as given over here, u1, u2, u3, and v1, v2, v3. Okay, and this notation is the notation to denote the cross product of u and b. Okay, so u cross b is called the cross product of u and b, and it's a vector. Okay, this is important. The scalar product, if you remember the dot product, it was a scalar quantity. Okay, so this cross product is going to give you a vector quantity and it is such that it is orthogonal to both u and v. Okay, so imagine that you have two vectors, which is also in the picture, you can just visualize it, and the cross product of these two vectors is defined to be the orthogonal vector to both of them. Okay, and it's going to look like this. Okay, so don't worry about this, it may look a little artificial to you, but we are just going to see how it be come up with this definition. Okay, so what we have u and b, and then vector orthogonal to u and b. Okay, so just look at the picture, you have this u and then this b. Now again you see here that there is a direction, the sense of direction for the angle also. So we are looking for the theta from u to b. Then u cross b is this vector, which is orthogonal to both these guys. Okay, so don't worry about these numbers which are written over here, I will explain what are they. Okay, so intuitively you should think that you have u cross b as orthogonal to u and b. So now we are going to specify that how does one get this form. Okay, and how to find the direction also. So then once we have the component form or the magnitude and the direction, we know the vector. Correct? All right, so just say that you have a vector w which coordinates x comma y comma z, and the two vectors are already given to you. So if I take this w to be orthogonal to u as well as to b, what I have, I know from our dot product definition that the w dot u will be 0 and similarly the w dot b will be 0, isn't it? So now you have got two linear equations, isn't it? And what you are trying to solve for, you are trying to solve for these two equations for x, y, and z. Okay, so if you do that, you precisely get what we had written, that e cross b is this guy. Okay, so you don't have to memorize this, you just think of that this is orthogonal to u and b, and this gives rise to two linear equations which are solved via this determinant, or I should say formal determinant rule. Correct? You could have written here x comma y comma z, but we are just trying to use the language of vectors. So here this is not really a determinant, because I, j, and k, they are vectors, whereas the other rows are rows of scalars. Okay, but what it does, it tells you that what are the components for I, for example. So component of I is going to be u2 b3 and then minus b2 u3. Similarly for j, you can do this and then this and this one. Okay, and similarly for k, and this is what you have already written here. Okay, so this is basically for convenience, you don't have to memorize any formula, you just have to solve for x, y, and z, the two linear equations. Okay, so geometrically what it is a vector which is orthogonal to both u and b. Okay, and how do you find the direction? Direction is basically given by the right hand rule. Okay, what does that mean? It just means the following. I'll just go back to the picture. Okay, so what you do is you hold your palm, okay, and turn your fingers in the direction of the theta. Okay, so you hold your palm, so it's like this, and then you turn your fingers in the direction of theta, and then your thumb is going to point in the direction of u cross b. Okay, this is what the right hand rule is. Okay, so this is important. If I hold the if I turn my fingers other way around, then I am going to get the downward vector. Okay, so that is going to be the negative of this vector. Okay, so that you have to keep in mind. So we know that how to find the direction of u cross b. We already have its component form, and we can just find its magnitude, isn't it? So magnitude, remember, whenever we try to find the length, we try to compute the modulus square. Okay, because the square root problem doesn't arise. So here it's simple, because it's just a vector, and then we have to just take the squares of the coordinates. Okay, so you do that, and then do this small computation, bring all the terms which has u and v separately, and then there are going to be cross terms, u1, v1, and so on. But if you just collect all these terms, what you are going to get, this is going to look like mod u square times mod b square, and then u dot b. Okay, because this quantity is nothing but u dot b, and it's a square, isn't it? Okay, so now what I'm going to do is I'm going to use the formula for u dot b in terms of the cosine theta. Okay, which is this, that u dot b was nothing but mod u times mod b times cosine theta, but there is a square, so you put a square here, and what you get by combining the two terms is just exactly this. Okay, so this tells you that the length of u cross b is given by length of u, then length of b, and sine theta. Theta is the angle between u and b, isn't it? So now this number on the right, the length, is actually having a very significant geometric meaning. Okay, so again we will we will come back to this. Let me first just talk one or two small examples here, or some brief properties which just follow from the definition. Okay, so for example, if I take I as a vector and j as a vector and try to compute its cross product. Okay, so you can see this, like what is the orthogonal vector to I and j? It's going to be the k vector. Now you have to see whether k or minus k, so you apply your right hand rule, you will get it has to be k. And if I change the order, then the direction is going to change. So if I take j cross I, so this is going to give me minus k. Now this is very important. You should notice that the unlike the dot product, where u dot b and b dot u, they were the same numbers, but here I cross j and j cross I, they are giving me different answers. One is k, another one is minus k. So this doesn't commute. If you change the order, you get a different answer. Okay, so these two just two examples are just to illustrate that this u cross b is not always same as b cross u. Okay, but what is it? It actually gives you that there is a minus sign. Okay, so now this here is a particular case which is telling me that I cross j is same as minus of j cross I. Okay, but here now I have generalized it. This is u cross b is equal to minus b cross u. Okay, so this proof requires some argument. Okay, this statement over here, it requires some argument. Okay, but what you can do is you can use the properties here and then prove this. Okay, or you can just use the definition. The definition is going to basically have interchange of the rows. Okay, and that will give rise to a minus sign. Okay, so this I am leaving a small exercise. And another thing is this is just the definition that u cross b is orthogonal to u, so this is going to be 0, the dot product. Similarly, the dot product with b is also going to be 0. Okay, but I would suggest that you try to prove it using the definition. Okay, you try to prove this thing using the definition of the cross product. Okay, and then the dot product here. Okay, and these three properties will be useful in doing this computation or this algebra. So everything is just going to follow using the definition of cross product. Okay, you just have to write down the definition and then one more line, and then you get the whatever properties I have written over here. Okay, so if I multiply, or if I take the scalar product of u with c, okay, or scalar multiplication, I should say scalar multiplication with u, and then take the cross product with b, this is same as I first take the u and then the scalar multiple of b and then the cross product. Okay, so you can just put the c wherever you like, and this cross is distributive over the addition, vector addition. So u cross bracket b plus w is going to be u cross b plus u cross w. Okay, so it distributes. So you decide which one you can compute easily first, and then you can do whichever side you want to. Okay, and similarly from the other side. Okay, now what is the advantage of these things? So for example, let us say that I want to prove this property which I have written here, u cross b is equal to minus b cross u. Okay, what you do is, we know that I can always write any vector u in terms of I, j and k, isn't it? And I have these properties that I cross j is k and j cross I is minus k. Similarly, you can find what is j cross k and what is I cross k, and so on. Okay, so what along with these three properties, what you will be left with basically scalars, which are going to be components of u, v and u and v, and I and j. So basically you have to just apply this distributive law, and then you will be just doing the cross product of these unit vectors. Okay, and then you collect them, and you will see that you get whatever you're trying to prove. Okay, okay, so now coming back to the magnitude, which was this number, if you remember. Okay, so the cross product u cross b has this magnitude, and this actually gives you the area of the parallelogram, which is determined by the two vectors which we have taken. Okay, how? Okay, so let us try to see this. So we have u and then we have v, and you just consider the copies of u and v and form the parallelogram. This we had been doing for some time now, so you know. Now the area of this parallelogram, okay, what is it? You just find the height, and then the base is mod u. Okay, now what is height? This is a right angle, this is theta, so you know that the height is exactly mod v times sine theta. Okay, this is just the triangle, right angle triangle. Okay, so and the area is going to be mod of u times this number, which is exactly this. Okay, so this vector, which is u cross b, and its magnitude is this, is basically telling you the magnitude or the area of this parallelogram. Okay, so this is how geometrically it relates to u and b as a perpendicular vector, and the magnitude is precisely the area of the parallelogram. Okay, so now along with this there is one more operation which kind of combines the dot product, and so basically what we do is we take now three vectors and call them u, v and w, and take this kind of product. Okay, this is called triple product, or sometimes people also call it triple scalar product. Okay, because this is finally going to give you a scalar quantity, correct? Because I have performed the cross product here first, so this is going to give me a vector, and then the dot product with u is going to give me a scalar, isn't it? Okay, so you can now we know that components of u and components of v cross w from the previous definition, and you can find the dot product. Okay, so in the component form you can express it. Okay, but that I am not going to do. What I am going to tell you that what is the meaning of this. Okay, so the meaning of this is basically is in this picture. So you take three vectors. Let us call this vector is u, and then this vector is b, and the vector here in the down, this is the bottom part of this is the w vector. Okay, so v and w, they are going to form this parallelogram, the base one. Okay, and the w is the in the upward direction. Okay, so what we need to see v cross w. Now v cross w, from our previous discussion, what is it? V cross w is going to be this vector, because it's going to be orthogonal to v and w both, isn't it? Okay, so and we know that what is it going to give me? It is going to give me the area of this parallelogram, the base parallelogram. Okay, so if I want to find the volume of this three-dimensional figure, which is called the parallelepiped, what is it? I know the area of the base, and then if I know the height, I just multiply them, isn't it? So this is basically this vector u and then the cross product of this. So this is going to give me a scalar quantity. If I take the modulus of this, it's going to give me the volume of this parallelepiped. Okay, All right, so how does that happen? Let us see it. So area, as I said, is just the magnitude of the cross product. Now you take this angle theta between this orthogonal vector to v and w and the third vector u. Okay, so the height you can compute now, because this height is just going to be because this, you know, this is going to be a right angle, so height you can compute is, it's going to be mod of u, because this is your u, and it's going to be cosine theta, correct? Sine theta is this one, so modulus of u and cosine of theta. Okay, so if I multiply to find the volume, so the volume of the parallel pipe is just the area times the height. So mod u cosine theta, this was the height, and the area was mod of v cross w. Okay, now what is this number? If you look at closely and use your knowledge of dot product. Okay, so just recall that the dot product of u and v, what was it in the modulus? It was just mod u, mod v, and cosine theta. Okay, so this is what exactly we have. So one vector is u here, other vector is v cross w. So mod of one vector, mod of other vector, and then modulus of cos theta. Okay, so this scalar triple product or triple product in its magnitude, or I should say in the absolute value, because this is just a number, is actually telling you about the volume of this parallel pipe. Okay, so these quantities are important. They carry some geometric meaning, and sometimes problems will be just, you know, to find what is the area or what is the volume of things given the vectors. Okay, so you have to understand that what and how to use the knowledge of dot product as well as the cross product. Okay, so this is just what I just said. Now okay, I mean as I said, I had not written u dot b cross w in terms of u1, u2, u3 and the other components, and you can do that. Okay, you can do that and see that, and you will realize that u dot b cross w can be computed by this determinant. Okay, so this is a determinant. Okay, because here everything is a number, and all the numbers you know, and you can find what is this determinant. Okay, so basically in one go you can just find what is the volume of the parallel pipe formed by u, v and w by just computing this determinant. Okay, now so this is kind of, as I said in the first or second lecture, that we will sometimes use some information about linear algebra. Okay, so these are the small details from linear algebra. Okay, because there you learned how to solve determinants, and you know, you learned some properties, so they will be used. Okay, so this is what I had meant when I was saying that some information, some ideas from linear algebra will be used. Okay, but try to come up with this. Okay, so first you just compute u dot b cross w using the components, and you see that this is exactly this. Okay, and you can discuss these things in your tutorial also, and see that, you know, how to use them. Okay, we are going to give you a lot of problems. Okay, and for this reason also you know, we have kept 2 sessions where we can meet. Okay, so that is why I am not trying to you know, solve problems here, because you know, that will be just talking to myself, but we will solve the problems in the tutorials and when we interact okay, online. Okay, and some other properties you can easily write down. Okay, so for example, if I am computing u dot b cross w, this is going to be same as I first look at u cross b and then dot product with w. Okay, so this you can, this, I mean, this one has to write it down, and you can just I mean, you can easily reduce these properties just following the definition, nothing else. Okay, and the third quantities, so remember the first quantity here both side is going to give you a scalar. Okay, the third quantity, the second property, which is now I am taking the cross product at both places. So this is a cross product and this is a cross product, so finally I am going to get a vector, and this side, this is scalar and then a vector, and then this is scalar and a vector. Okay, so I am going to get a vector on this side also. Okay, this property may require a little bit of extra work. Okay, but it can be proved if you just follow the definition. There is absolutely no trick or no non-trivial calculation. Okay, it just follows, but right now I am leaving it as an exercise so that you write it down and then use all the properties. Okay, this will use your most of the properties which we have learned. Okay, so unless you start writing yourself, there's no way that we can learn things properly. Okay, so that is why this is left as an exercise, and if some of you don't get it, please discuss it, okay, in the tutorial. Okay, I will also have this as a problem in the tutorial. Okay, but this is just writing it down, that's all. Okay, and note that here also we are taking product of three things. So okay, sometimes in book you will see that this is being referred to as the vector triple product. Okay, because three vectors and being taken, we are taking the cross product of them and we are getting a vector, correct? So sometimes this quantity is referred to as the vector triple product or triple vector product, whichever way you. Okay. Okay, so with this much of information about vectors, we can talk about the some geometric features like lines and then planes and so on in terms of vectors. Okay, so what I'm going to do is next I'm going to discuss equations of lines and so on. I just take a small break and then we resume in 2 minutes. Okay.